Hello everyone, pleased to meet you. My name is Simone Aonzo and I am an assistant professor at EURECOM. Today I will present humans versus machines in malware classification that is the result of a joint work with INRIA, another research center in France. So this work is about malware analysis and the humans are the malware analysts while the machines are machine learning algorithms. Let's start. Okay, as I said, in the malware analysis process, the malware analysts are the expert humans in charge of analyzing the malware. And a very common task for them is the binary classification. So they got a sample and they have to classify if the sample has benign or malicious purposes. What they do is that they often resort to sandboxes that are isolated environments in which they plug and they run and they execute a sample, and at the end of the execution, the sandbox reports the dynamic behavior of the sample in addition to the static properties of the file. For example, libraries, the imported libraries. However, we have a problem because the number of analysts cannot be scaled up to cope with new cyber threats. And therefore, the scientific community, and I think you are well aware of the vast amount of research that has been conducted in recent years, they have tried to solve this problem. And what do we do is that we tell the machines which bytes, which features they have to extract from a sample or from the sandbox report, and then we teach the machines, hey, this feature vector, malware, goodware, and so on and so forth. Amazing, but again, we have a problem. The problem is that machine learning works great in applications like, speech, text, image detection, because the pronunciation, characters, objects, real-life things, they remain relatively constant over time. On the other hand, in this case, malware is the perfect adversarial context because the only limit is the imagination of the malware author. And so, think about it, you have to predict if a sample is benign or malicious, and maybe that sample has been created with the purpose of evaded detection. It's a very hard task. So, the research question that led our work was, what information guides the decision-making of human and machines when they are classifying samples? Because maybe we can learn something from each other. Maybe there are some features that we are not encoding properly, still encoding properly, or maybe machine learning algorithms, they found a way to better classify sample looking at some specific features. We did not restrict our study just by comparing humans and machines, by the way. We also compared experts with novices, senior experts with young experts, machines, and finally, humans versus machine. Finally, I have to, for the sake of clarification, I have to say that we focused our study on Windows malware and therefore our samples that they follow the portable executable file format. Okay, we were able to recruit 110 humans, 38 experts that comes from famous cybersecurity companies and academic researchers, and 7 among them, they have more than 9 or more years of experience. 72 novices, they were mainly students and some beginner CTF players. The only requirement for the novices, they have attended at least a malware analysis course, so they have an idea of what they were doing. Then we chose two state-of-the-art machine learning algorithms. The first one is random forest, and the second one is CNN. We chose them because they provide diversified perspectives of the classification boundaries. So, in the end, what we did? We created a game. We designed a web game named Detect Me If You Can. Given the fact that it's just a website, we were able to reach many people across the globe. The design element of this game are the leaderboard And there are many papers that shows our competition through gamification, they have a positive motivational effect on individual and their overall performances. And points, because we need points to create the leaderboard. What do they have to do? Is that they have correctly classified 20 sample, 20 virus total reports. For the sake of precision, these virus total report, they were containing also the dynamic behavior, so not just the static, not just the report of the engines. There was think about it like, you know, a complete sandbox report with all the properties of the files and the dynamic behavior recorded. They had to do it using as few features as possible, because we wanted, you know, to create a ranking. We wanted to see how humans, they prioritize these features. And therefore, the players, they have to buy a feature. So they have to sacrifice some potential points to get information and to get a higher score. Unfortunately, I do not have time to explain you the scoring mechanism. The only thing that you have to keep in mind is that it was crafted in a way to promote a correct classification. So it was the best strategy was to use enough information to make a confident decision. Now I will show you the user interface of our game. Starting from the top left corner, we can see here that the player is looking at the third sample out of 20. The experiment was limited in time. They had maximum 1 hour. And to give you a rough idea, the experts took on average 30 minutes, while the novices on average 45 minutes. And here you can see that this player, so at the very beginning of one round, when they are looking at one sample, they start with some basic properties that basically give no information, just saying how the size, giving the size of the sample. And then if they want to look at more data, they have to click on the left bar on the feature they are interested in looking at. So in this case, this player bought 3 features, sections, network, and runtime DLLs, and as you can see, it means that he sacrificed 3 points for trying to classify this sample. Also, as a note, as you can see here, these processes and services strings, they have a strike through because the player clicked on it, and this feature was empty. So it means that that feature was not available because some samples, for example, they do not perform network activity, and in this case, it did not interact with the system services. In this case, we do not remove any point. Otherwise, you know, it could introduce a bias in the strategy of the player because maybe they think, oh, maybe this feature is not likely that I'm gonna watch it, and so it could have biased our results. In the end, when a player has got enough information to make a confident decision, he has to click if the report was a malware of a goodware. Okay, finally, let's see some results. Let's see what our participant did. Let's focus on the median values because they are very similar to the average. What we did is that we ran some statistical test, precisely the Welch t-test, to see there was any statistical difference among experts and novices. And it was the case in the time needed to complete the game, the final score, the number of right answers, but not in the features. The number of the feature used, the unique feature used during the game, you know, it was looking like that the features was almost the same for both categories. And that was also the case for senior and young experts. So we investigate further, and in this plot you can see on the x-axis the features used. If you see a dagger at the beginning of the string, it means that it is a dynamic features, and on the y-axis how many times that particular features has been seen during a game of, you know, the expert or novices. The only difference here, as you can see, is that novices had got more importance to virus total labels. We used some virus total labels because we also wanted to study how to react in case of a false, true, positive or negative. Unfortunately, I do not have time to go into this detail. But you know, as you can see here from this table, looking at the most used top 5 features, irrespective of the fact that were used for a correct or an incorrect classification, the features are always the same, both for experts and novices. It means that it is only the way that they interpret the data, thanks to their experience, that makes a real difference. Then we created an experiment for the machines. So we created a balanced data set of about 22K virus total reports. Obviously, following the good practice of machine learning, families were overrepresented in the malicious data set and so on and so forth. We did not develop another classifier. We just used, state-of-the-art encoded techniques, everything well known to the community. We evaluated the performances of the two ML players via 5-fold cross-validation test. 80% of the benign malicious samples reports were used to tune the model parameters, where the 20% as the test set. And the averaged AUC scores that we got, they were more than 0.99 for both algorithms. Great, now we have the model, and we use that model to play our games. But keep it in mind that the machines, they had all the feature advantages. So they had all the features available at the same time, while the humans, they had to prioritize the features. We did another experiment in which we tried to remove some features, but the situation got worse. More details in the paper, by the way. And obviously, we excluded the features related to virus total, because we used the virus total to choose the reports, and that would have introduced a bias in the experiment. So what we got is that the human expert, as I said before, the average equals to the median. They got 6 answer correct out of 20, 16 answer correct out of 20, while machines, 17 for random forest and 16 for CNN. So let's call it a draw, and we also looked at why, on which samples, on which reports they commit the most mistakes. The point is that both ML algorithms misclassified the same 2 samples, but they were not among the most difficult samples for humans. So in general, the misclassified samples by machines and humans are different. This is exactly what we were looking for. So we adopted a SHAP as a model agnostic explanation tool. We didn't use the recursive feature elimination of using out-of-bag error of random forest, because that method is prone to overestimate the importance of high cardinality categorical variables. And we got the ranking for random forest, CNN, and our expert humans. The takeaway from these pictures are that in a bizarre turn of events, the resource features that rank the top for machines were ranked last by expert humans. Same thing for the processes. And we saw that there was a clear preference for static features for machines and dynamic features for experts. So let's wrap up together and let's go to the takeaways of this work. So as I said, as we have shown, the experts and novices, they decide using the same features, but also do the senior experts. And during classification, experts use more features, while novices made the majority of mistakes, because we must teach to the students that you have to rule out all the possible signs of bad intention. So it's harder to classify a goodware than a malware. Humans and machines agree on the importance of 2 features, that is the network traffic and a valid digital signature. And the machines rank top resources while human last, because malware authors, they tend to embed malicious resources in the resources. So please always take a look at it, malware analysts. I'm rushing. Our experts were able to classify using by less than 1/3 of the available features with a preference for dynamic behavior. And while machines, they prefer static features because the dynamic features are always missing. So this is an interesting future research idea. We should be able to semantically recreate meaningful feature in order to replace missing features in the dataset. Our work has also impacts on the human-computer interaction. we argue that modern sandboxes must show OSINT data, so IPs and domains, because humans, they always try to look for external sources of this information. And the sandbox must also show what are the most important features that help to classify the sample, so that the analyst can bridge the cognitive gap that we've shown so far. Thank you for your attention.